After the last tutorial, we received some questions from you guys. So I don't know, maybe we went a bit too far with this, maybe we had some wrong assumptions, but I just want to take these questions and turn them into kind of a repetition of what we did during the past tutorials and talk over some of the very fundamental tools and techniques that we use when writing VEX code. First, I want to talk a bit about accessing setting attributes and about for each loops versus wrangles. So let's just drop down a grid for that, and we'll be working on this grid here as an example. And I don't think that we'll be able to turn this into any production setup, so it's just for demonstration purpose. Let's just disable lighting here, have this grid here, 10 times 10 points. So in the end, when we middle mouse over this, we have 100 points, 81 primitives. So a primitive is each of those squares here. Let's first repeat some of the very basics when accessing or setting attributes. Just going to drop down a point wrangle here and say I want to move all those points up along the y-axis here. They are now sitting on the zx plane. That means they have a y value of 0, which you can also see when you dive into the geo spreadsheet here, and you can see the y component of my position vector p is always 0. There are several ways how I could access and set this attribute on the points. The most compact and simple way would be using the @ syntax. And to make it a bit more clear what's happening here, let's create a vector and call it pos. So this is just internally in my wrangle. It's a variable called pos and it'll store a vector. And now let's assign a value to this variable pos here. And what I want to assign is the position p, which I can access with the syntax @P, like so. No error, nothing happens. What I just did there is from each single point, I looked up each individual point's position and stored it into this variable pos here. And I'm a fan of writing this a bit more explicit because there are some times where this is not explicit enough and Houdini might throw some errors. So what I want to do is add a small v in front of my @P syntax, which will explicitly tell Houdini and VEX that the type coming in through this @P syntax here is a vector. So 3 individual values, one for x, one for y, one for z. So far. Now, what I can do, or what I want to do, is add to this vector, but only add to its y component. And again, there are several ways how I could do this in VEX. On the one hand, I could take my vector pos and tell VEX that pos is equal to the current value of pos plus, let's create a static vector here, 0, 1, 0, like this. So what I did here is I took the variable pos, which stores a vector, and tell VEX that the new value of pos equals to the old value of pos plus this constant vector here. So we're adding nothing along the x-axis, 1 on the y-axis, and nothing along the z-axis. So we're only moving this along the y-axis upwards. However, as you can see when I click outside of the code editor, nothing is happening. That is because I only changed my internal variable that I created here in VEX called pos. However, for Houdini to actually do something with the geometry, I have to write back the new values onto the point attributes, in this case onto my positional point attribute that stores the point's position. So let's do that. So I have my v@p, that's the @ syntax for accessing the point's positional attribute, and I want to set that to the value that's stored in my variable pos, like this. Finish off with a semicolon and click outside of the editor, and I can see now I moved the whole plane up because I moved every single point plus 1 along the y-axis. Let's just copy this point wrangle here, paste it there. And in this point wrangle, let's go over another way of adding to this position here. So instead of writing this here, let's delete it. I can directly access a vector's components individually. So I can access the x, y, or z component like this by writing down pos.x, pos.y, or pos.z. And in this case, I just want to add to the pos.y, and I want to set the pos.y to my previous pos.y plus 1. Let's click outside, and you can see again nothing changed because I'm again moving the grid up 1 unit here. I can change that just so that you can see this actually does something. Okay, let's set it to 1 again, like this. There's another syntax how I can access a vector's individual component, which stems from the fact that a color is also a vector. So with a color, you would access the first component with an R for red, the second with a G for green, and the third component with a B for blue. So I want to access the second component here. So RGB, that would be G in this case. And you can see, same thing, just works the same way, and admittedly this syntax is a bit weird for a position. However, in colors you might want to resort to it. There's yet another way how you can access a vector's individual components, which is with a syntax very similar to an array. So in an array, you would access the array elements by just calling them with their indices in square brackets. And a vector, in a way, for a computer is nothing more than an array with 3 values. So I can access the first value with an ID, an index of 0, like this, a second value with an index of 1, and the third value with an index of 2. So I want to access the second value, like this, and I can see this too is working as expected. So these were 3 ways of accessing a vector's individual components. However, when I look at this formula here, this is kind of clumsy, and I already mentioned it, we can kind of shorten this. So instead of writing pos.y equals pos.y plus 1, we could get rid of the second pos plus y by using this shorthand here, pos.y plus equals 1. So that tells Vex to take the old value of pos.y and add to it 1. Again, this is working as expected. However, what we can also do, and there is no need for us doing it like this here, what we can also do is directly add this 1 to the p component here without storing the current p in another variable and then writing it back. So we can just basically put all of this into one line. Let's copy this point triangle here, paste it there. What we can do is, we can, instead of writing pos.y here plus equals 1, we can just add v at p here, and then just delete that because we don't need to read that out into another variable. And also delete this line because we don't need to write back the variable we have not created efficiently now. Like this. So all I'm doing here is read out the positional y component and add to it a 1 like this. As you can see, again, this works as expected. So in one line we are basically reading out the positional y component, adding 1 to it, and writing it back onto the attribute. Let's do the same thing for color. Just copy this grid and add a point triangle, highlight it. So Houdini's built-in intrinsic attribute for displaying and storing color is called CD, capital C, which means color diffuse. It's for shading. So again, what I could do here is use my very short expression here, and I want to load in a vector, 3 components, add CD, and let's just set it to something. In my case, let's maybe go for 0.8, 0.4, and 1, like this. And I can see I get this weird purple. Well, let's start it back a bit like this bluish color here. And some of you asked if it makes sense to use a for each to iterate over each of those points. So let's just try that and drop down a for each point here. So what that will do, and when I highlight it, you can see that it'll isolate the points. And also when I check single pass, you can see in a bit more detail what we're doing here. Let's just increase the point size so you can see this point here. So each iteration, each time this loop is being run, we're going to isolate one single point and then execute whatever is in this loop here on this single point. And let's just add an add here and delete everything but the points before we feed that in to both my point triangle and the for each here. So you can see I get these purplish points here. Maybe let's increase their contrast a bit. Like this, these green points. So in here what I have, then let's just look at a single pass for now. What I want to do is set the point's color value. And of course, I could just copy this over and then just again set this to run. Same result here. Let's merge both and run a bit of profiling on this. Let's just highlight the grid here so that we can actually see something performance-wise, performance difference-wise. Let's increase this to say 500 times 500 points. So when we middle mouse on it, we have 250,000 points here. Let's go to the performance monitor, hit record, and what that will do is it'll record how long each of those nodes takes to execute. Let's hit merge and wait a bit. So that is the result. Let's scroll down a bit here. And you can see my whole for each loop took on the one hand 5 seconds and 9 seconds. That sums up to 14 seconds. And then the point triangle took another, well, 21 seconds. So we're ending at 35 seconds for this version here. 35 seconds to change the color on 250,000 points. And my point triangle 4 ran for, well, 1,000th of a second. That is because my point triangle by default is set up to do what the for each is doing here, just much more efficiently and multi-threaded. So what the point triangle does is, when you just wire it up like this is, it isolates each single point and then runs whatever code you write in here for this single point. Basically what you're brute forcing here with your for each loop. And some of you might say, well, yes, the for each loop by itself is not the fastest thing, but there are compile blocks. And with those, the for each loop really flies, which is correct in a way. So let's also add those. Just copy this for each block here, paste it. And let's just disable the update here for a short while I fix this. So what I want to do is add compile blocks. Like this. Just in the beginning and at the end. Let's clean this up a bit like this. And after I added the compile begin and end block, I just want to go into my for each end and check multi-threaded when compiled. Now let's just wire all those in here again into the merge. So we end up with something like this. Let's again check auto update and again go to the performance monitor, hit record and just highlight the merge and wait a bit. Now that we can see the profiling results, we again see that this version here adds up to 5 plus 9 plus 21, 35 seconds for this here. Then with the compiled version, you can see the overall time at the compile insop, which is 2.5 seconds, which admittedly is miles faster than the standard for each SOP. However, when you look at the times for our point wrangle 4, it's so fast Houdini has problems even measuring it. This is one of the prime, if not the prime reasons why I try to stay away from for each loops in SOPs. Even when compiled, they are just darn slow and most of the time slower than anything you could cook up in Vex. Let's stop this and look at other ways of iterating through your geometry. Okay, again what I have here is the incoming points of that grid. And just now for the sake of speed, let's dial this back to 100 by 100 here and add another, in this case, an attrib wrangle. And an attrib wrangle is just the same thing as a point or detail or primitive wrangle. It is just not typed, so you can just choose whatever you like to run it over. And you can do that in the point wrangle or in the primitive wrangle as well, as you can see here. So again, let's just copy the color command out of that wrangle here, paste it in your attrib wrangle, and now it's set to run over points. So for each point it'll execute this code here, which will give us something like this. Yes, of course, that's what we expected. However, there are other ways of accessing and setting those attribute values here, such as the color. So let me just comment this out. And by default, when run over points, Houdini and Vex knows the current point number and stores it in an attribute called ptnum. And for primitives, this attribute would be called primnum, like so. So whatever point or primitive, set to primitives, we'd be working on in this wrangle here currently, it'll be stored in ptnum for points or primnum for primitives. And we can use that knowledge to use a function to actually access any attribute that we store on a given point. So let's read out a color, create a vector call, and set it equal to. And now let's use the point function to read a point attribute. And this function for primitives would be called prim, like this. But we're working on points now, so let's use the points function here. So points takes in several parameters. When you go in the middle of this function name and hit F1, we open up Houdini's help browser here, and we can see this takes in 3 parameters. Your geometry stream, the attribute name, and the point number we want to read from. So the geometry stream specifies which of those inputs we're reading from. Currently we're just having geometry coming in through the first input slot here, and this is input slot with ID 0, so 0, 1, 2, 3. To read the color using the point function, let's specify the first input slot, then the name of the attribute that we'd like to read, in our case CD for the color value, and then the point number of the point from which we want to read the attribute. And as mentioned, we're storing the current point number in our attribute called ptnum, like this. So nothing happening there. Let's just do something with this. Let's just take the vector color and add to it fixed value, and why not use this one here. Again, not much happening because we have to write it back, and of course we could use our badd cd equals to call. That would work, yes. However, let's use a function for that, and the function to store back or write back a value onto a point is called set point attrib, like this. Again, when we have a look at the help, we can see this one takes in 5 arguments, with this one here being optional, so you can actually shorten it down to those 4 arguments here. The geometry where the points are coming from, again this is slot 0 here. The name of the attribute that we want to store, point number on which we want to write back the new attribute value, and then the final value that we want to write back. Let's do this. So we want to write back on points coming into the first slot, so that's the slot with the number 0. We want to write back the attribute CD. We want to write it back onto our currently active point. That's the point with the point number at ptnum. And we want to write back the value that's been stored in col, like this. Some of you might ask yourselves, why would you go through this length of code to actually write back values or read out values? Well, because sometimes you're reading values not from the point that you're currently working on, and you don't want to store them necessarily on the point you are currently working on. So what we could do, for example, instead of adding ptnum here, we could just add a fixed number, for example, 0. So now we are only writing back the color value onto the first point, or, I don't know, 170. So now we are just writing it back onto this point here, or 770. So the point and the setPoint attrib and the prim and setPrim attrib for primitives are two fundamental functions that we oftentimes use, and we use them when we want to try to access or write back point or prim attributes onto points or prims which we are currently not working on in this loop that's executed in our wrangle. And by loop, I mean just the fact that this wrangle is set to iterate over the points when set to run over points, or primitives when set to run over primitives. So basically this has its own built-in for each loop, if you like so. And this point and setPoint attrib or prim and setPrim attrib function really gets helpful when you set your wrangle to run over detail only once. So what I want to do is I don't want to read in the color, I just want to create the color vector, which in our case results in the same image. So if I try to add back at ptnum in here, I can see this does not work. Because now what I've done is I basically set up this wrangle to run only once, so there's no internal for each loop that's being run for each of these points here. So I have to cook up my own. And one way I could do this is first get a list of all the points coming in here. And I could abuse a function called expandPointGroup. So what I'm going to do here is I create a list, an array. Let's call it PTS for points, square brackets to indicate it's an array. And I want to fill it with all the values that are being returned by the function called expandPointGroup, which then takes in, if you hit F1, 2 arguments, the geometry and the group name. So the geometry again is 0, the first input slot, and the group name is nothing because we don't have a group yet, so we want everything in there. And just for the sake of debugging this, let's write that out. I square brackets for an integer array at PTS equals PTS, so I just wrote this out as an attribute onto our details here, detail attribute. So let's head to our geo spreadsheet, and in the details I can see I have a list of all my points coming in there. And now what I could do is, down here where I set the point attribute, I could drop down a for each node, like this, and out of my PTS lists I will take out each element and write it into an integer variable called, let's call it PT there. And now what I can do in the setPoint attrib, I can exchange my ptnum with the variable pt that I just created. So what we're doing here is for each iteration of this loop, we are taking one element out of PTS, putting it into PT, and then executing some code here. And in this case, I'm just setting the point attribute on my geo coming into the first slot. Point attribute is called CD, and I'm setting it on the point PT, which we extracted from PTS, and we'll set it to the value stored in color, like this here. Okay, we can see now everything changed to green because we wrote a list containing every single point of this geometry into PTS, and now we are just taking out the single points and setting their color value here. If we take a closer look at the geo spreadsheet and at the values stored in this PTS list here, you can see they are really simple. They go just from 0 to basically the number of points that you have minus 1, so 9,999 here. So it kind of isn't worth going through this hassle with expanding the point group, which takes a bit of time, and setting up a for each loop, which is kind of a very elaborate way of iterating over a few points here. So let's just copy this attrib wrangle that's set to detail here, and let's exchange it. There is a more simpler loop to actually execute this function here on every point. So what I want to do is I want to delete those 2 lines where I created the array, and I also want to delete the for each loop here. All I have to do is count from 0 to the number of points minus 1. And again, Houdini has a built-in attribute that tells me the exact number of points coming in through my main slot, that is my first slot, which is called at numpt. This stores the total number of points coming in there. So what I want to do is I want to create a loop that's running from 0 to numpt. And this can be done with a for loop. the much simpler version. So like this. A for loop needs a few things to be set up. On the one hand, it needs a counting variable. So the variable where it stores the actual iteration number. So how often it has already been executed. And this is basically the thing that counts from 0 to 9,999 in our case. And we should initialize and declare it. So it's an integer. Let's call it pt. And let's start with it being 0. Next, we want to drop down the condition, which we want to check each iteration. And if this condition is true, we keep on iterating. So we only want to keep this running and keep this iterating if pt is smaller than our pt num here. So if it's below 10,000, so that it just goes to 9,999. And then we want to specify what we want to do with pt after we run one iteration. And in our case, we want to increase it by 1, which we can write in a shorthand version, pt++. So let's keep our fingers crossed. And I just discovered that when I set my wrangle to run over details, I don't have access to this pt num. So we'll have to find another way of getting the number of points coming in here, if I don't want to type in that number manually each time I change something in my geometry piping in there. And I guess there's a function for that, and it's called endpoints, which just returns the number of points in a given geometry. So again, let's try that. Call it integer num, and it should be equal to endpoints coming in through my slot 0 here. And then let's exchange the 10,000 down here with the num. Okay, now that's working. Let's try and change the resolution of my grid a bit. Yeah, still working. So basically what I wanted to demonstrate here are on the one hand the two possibilities to set up your own loop when you're working within an attribute wrangle that is set to run only once. And on the other hand, I wanted to show you that these functions, endpoints, set point attrib, or expand point group, or even point to read out the attribute's values, are quite helpful. They might not seem to make sense at first when you're only looking at wrangles in a point wrangle context and in a context where you only want to work on the currently active point. However, as soon as you're working on other points or working with other types of wrangles than a point wrangle, they become really useful and really important. I'd like to finish off this repetition with two exercises. And along the way, I'd like to talk a bit about the steps involved in coming up with an algorithm. So the first thing I want to do is implement what's called a catenary arc. And a catenary arc is the shape that a wire or a chain forms when it's just hanging under its own weight in gravity, being suspended on 2 points. And let's assume you don't know anything about catenaries, and someone approaches you and asks you to implement a catenary for whatever reasons. So of course the first sensible reaction is to fire up your browser and then just Google catenary. Yeah, I'm on German Google here, but let's assume you're on an English Google, so it'll most likely spit out this Wikipedia entry about a catenary. So there are some quite nice examples of the shapes that catenaries form. There's a bit of a short description what catenaries are and how they were described and studied. And when I look at the contents, this one gets me interested here. Mathematical description and equation. So let's just head there. Because in the end, what I'll do in Vex is just implement a mathematical model of this. And here's another thing that some of you guys asked. Writing algorithms and coming up with algorithms is only partially to do with knowing a programming language or knowing Vex in particular. The other part is being able on the one hand to cope with mathematical formulas, but that's actually not the major part in my opinion. The major part when coming up with algorithms is being able to solve logic riddles, because that's what it is. And in my opinion, this is a skill that can be learned or intensified only by practice. So it's a habit you have to get yourself into. There's very little in the way of actual reading or watching videos. This is just you yourself trying to solve a logical riddle. Okay, let's try to solve this logical riddle of the catenary curve together. So mathematical description. Equation. The equation of a catenary in Cartesian coordinates has the form blah. First thing here is Cartesian coordinates. That's a good thing. That is just saying we are working on a right-angled coordinate system like the one we have in Houdini. In computer graphics, this is your standard coordinate system and we are hardly used to anything else. However, in math, there are a bunch of other coordinate systems. So this is important for mathematicians, not for us. So the equation has this form. Y, that means the position along the y-axis, the vertical position, is equal to a times cos h of x divided by a. What is this cos h? Well, it says in the next line where cos h is the hyperbolic cosine function. And Wikipedia even goes so far as reshaping this hyperbolic cosine function into this form of functions. So if you don't have a hyperbolic cosine available, you can just reshape it into that. However, Houdini and Vex offers a hyperbolic cosine, so we can just stick at this here. there. So what is a? I mean, we are aware what x should be. It's just a position along the x-axis. But a, well, they have this nice graph here, different values of a. A is basically a scaling factor that tells the equation how deep the catenary should hang in a way. So when looking at this, another thing that occurs to me is that for this catenary, so if these are the points that the chain or wire is fixed on, for these catenary curves, the coordinates along the x-axis are always symmetrical. So this is about, let's say, 2.4, and this is minus 2.4. So here's the other thing that we have to take care of. We have to make sure that the coordinates on our wire that we want to reshape into a catenary wire go from, let's say, minus something to plus something, and to keep it simple, let's just reshape them into going from -1 to +1 all the time. So the only factor driving the appearance of my catenary arc then is the value of a. And this is about all I have to know to implement this. So let's head over to Houdini and let's drop down a geo, and in there just drop down a line, which we're going to use as our basic line to turn into a catenary. Let's just have this along the Z direction. Doesn't matter if I have it along the X or Z direction. And let's just have 24 points in there, which I can then move around. Okay, let's drop down the point wrangle. So in here, the first thing that I have to do is get this X value that I plug into my equation here. And don't get confused here. The x value, in this case, does have nothing to do with the position. So even if all my x values here, in this case, would be 0, and let's have a look at the geo spreadsheet here to clarify. So all of my x values here are 0. Even though this is the case, I can still calculate this formula. What I'll have to do is, I will have to find x by looking at each point in the curve and finding out where it is in regard to the start and end point of that curve. So what I want to have in the end is an x value going from -1 on this point to 0 on the center point to +1 on the other end point. What we could do, of course, is write a bit of code to come up with that. However, let's make our lives easier by just dropping down a resample node in there, and in the resample node, let's check curve U attribute and let's uncheck maximum segment length. So we're actually not doing a resample here, but when we middle mouse button on this, we just created a curve U attribute. Let's go to the geo spreadsheet. So the curve U just goes from 0 on the first point to 1 on the last point. So that's already getting us there half the way. So there's another thing we need to talk about: when to use Vex, when to use built-in Houdini SOPs. There is no fixed recipe for that. Sometimes if you want to do something very elaborate, for example, extruding polygons, Houdini most of the time has decent built-in SOPs for that, so let's just use those instead of implementing a very complicated algorithm there. However, if you run into troubles where you either don't know or don't find the SOP doing a certain thing, or if that certain node turns out to be extremely slow, then it can be worth going through the hassle of actually implementing the same function in Vex. This is basically something you can judge easier the more experienced you are. It's just a matter of using Houdini and finding out what's in there and how quickly it works. So back to our scene. We have now a value ranging from 0 to 1. However, we'd like to remap that into -1 to 1. So let's just do that in here, and we want to read out the curve U attribute that we just set, and let's just set it to a value that we remap. So let's use the fit01. Fit01 expects an input value ranging from 0 to 1, coming in through this attribute, curve U, and it remaps this to a range that we tell it to, in our case -1 to 1. Like this. Let's go back to the geo spreadsheet, and now we can see the curve U ranging from -1 to close to 0 to 1. And here's another tip. So if at some point you don't know exactly what a function is doing, or if you have the feeling that we went over the explanation too quickly, just go in there, highlight the function name and hit F1, and you can read Houdini's help file regarding this function. So in this case, what we're taking is the value of this attribute, which should be in the range of 0 and 1, and we're remapping it to range from -1 to 1. However, what we want to do with this value is we don't want to store it on the curve U, so we don't want to write it back. This should actually be our x value. And now let's plug it in this formula here. We also need an a value. Let's create that. Float a equals 2. And let's have a look at the Wikipedia. Yeah, something between 1 and 2 looks nice. So let's set the a value to 1.5. And this is just from this diagram here, just trying to figure it out. Okay, finally, let's calculate our y position. Float y equals 2. And now we have this formula here, a. And if there's no symbol written in between two variables or a variable and a function, that always assumes it's a multiplication. So a times the hyperbolic cosine of x divided by a. That's just this. Okay, no errors so far. So after we calculated this y position, let's also change our points y position by just adding it. So let's use a shorthand syntax. Be at p.y plus equals y. We can see now we have this catenary arc up there, and let's just change the value for 1. Yeah. We can see we can change the appearance of the curve there. However, depending on our value for a, my curve now jumps in space upwards. So how could I compensate for this? Well, depending on the different values of a, it jumps to a different position here. So I guess there are several things we could do. However, what I ended up doing is just calculating a y value for the first point and then subtracting this value from each and every point. So just as a correctional factor, so to say. Because when I look at this, the y value on the first or at the last point, wouldn't matter in this case, is the biggest y value. So that's the biggest amount we offset this whole curve. So if we subtract this from the overall curve, we will move it back to its original point. So let's do that. Let's calculate another float. Let's call it core y, correctional y, and it equals to a times the hyperbolic cosine of, and I said I wanted to use the first or the last point, so that's either an x value of -1 or 1. Let's just go with 1 divided by a. Finally, let's subtract that from the position. And now we have our curve back at our original y position here. Now to make this a bit more user-friendly, I want to have a slider for the a value. So let's create that using the channel float function. And let's just call it a. Create that user interface for that. Drag this down a bit. And now I can dial in a value for a down here with that slider. So that is a catenary. Again, cooking up algorithms is unequal parts being able to read a mathematical formula, figuring it out, being able to work through a logic riddle, some sorts of, and then finally being able to use the tools to implement that logic riddle, which is what we're trying to mainly focus on in the VEX 101. And again, to really excel in this and to know which tools to use at what given time requires a bit of experience. Experience you can only gain when working with this. So I think kind of the painful but encouraging point here is, although it might not feel like this or it might not look like this at first, while trying to sort things out and while struggling your way through, you will get better at the stuff you're doing. It's just one thing that I personally realized when trying to re-implement a paper that I looked at a year ago and wasn't able to figure it out. And a year later, I was finally able to basically read through it and then just implement it away. So although you might not notice it in the process, when looking back at it after a certain amount of time, you will see the massive progress you're making. So don't be discouraged.